I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on a Newton's second law experiment called a modified Atwood machine. Alright, so what an Atwood machine is you have a pulley and you have a rope over that pulley, and you use that to, farmers use an Atwood machine to lift bales of hay up into the hay loft. So you have a weight pulling and the pulley system pulls it up. So we've modified that. So we have a hanging weight off of the end attached to a car that is horizontal. So we have this weight that is going to cause this car to accelerate. So we're going to go ahead and make some observations. So go ahead and pause the video, write down all your observations that you saw, and we're going to go ahead and show you what some of my students have made in terms of observations in the past. Alright, so you can see some of the observations that my students made, and hopefully you made some of the same observations. The car sped up. Okay, so the car sped up. So what we're going to do is we're going to draw a free body diagram for that car as it speeds. So let's go ahead and pause the video, draw a free body diagram for that situation. So the first step in drawing the free body diagram is drawing this. What we're going to do is we know that the string is directly in contact with the car. That supplies a tension force. We know that the ramp is in contact with the car. That supplies a normal force. And we've done something to modify the situation so that there is no friction. So we actually canceled out friction. And we know that the earth supplies a gravitational force. And notice that the weight, the hanger does not have any interaction with the car. We know that the hanger and the string have an interaction, which is a tension force, which is the same tension force as we have up here. And then we also know that the earth supplies a gravitational force on the hanger, and the ramp is not in contact with the hanger. So we're also going to draw a free body diagram for the hanger as well. And we have three forces that are acting on it. We have the tension force, we have the gravitational force, and we have the normal force. So we know that the normal force points up and the gravitational force points down. And from the video, you can see that the tension is pulling to the left. And for the hanger is accelerating downward, which means that we have this gravitational force on the hanger, but the upward force of tension is going to be smaller because it is accelerating downward. Okay, so we have this acceleration going on for our free body diagrams. We can see the car is accelerating, and we can see that the hanger is accelerating. All right, so we could see the free body diagram. So one thing that's always a question is there friction? Is there not friction? So what I have done in this situation is to help balance out friction. This ramp is set such that when I push this car towards the pulley at the end of the ramp, that it moves at a constant speed. So that way I know that when the fishing line is pulled taut with the hanging weight off the end, I know that that is the only force that is causing it to accelerate, which is what we're looking for. Okay, so some of the observations we can make. So let's go ahead and let's go to the whiteboard. So here are some of the changes that we can make based on the observations that we had. Is we can change the mass of the system, we can change the weight of the hanger, and we can measure the acceleration or calculate the acceleration from the time of the free falling hanging mass. So what we're going to do in this video is we're going to change the mass of the system. So that means the mass of the system is not only the car, but the car plus the hanger. So we're going to take the car, which by itself, the mass of the car is going to be 0.5 kilograms. And the mass of the hanger is going to be 50 grams or 0.05 kilograms. So the initial mass with nothing on is going to be 0.55 kilograms. And what we're going to do is we're going to add 0.5 kilograms each time to that until we end up with a mass of 5.05 kilograms, which means for the situation, we have to keep the weight of the hanger at control. But we need to know the value of that control. So the controlled value of the weight of the hanger, since there's 50 grams on the end, the weight of the hanger is going to be the mass of the hanger times G. So the mass of the hanger is 0.05 kilograms times 9.8. Remember, we're in the lab, so we're not going to use 10. So that's newtons per kilogram or meters per second squared. We end up with a measure in newtons, and that controlled value is going to be 0.49 newtons. So this is going to be your controlled value. You're going to change the mass of the system, and you're going to calculate the acceleration from. All right, so we can see that one set of groups is going to be working on one particular lab where we are going to keep the mass of the system, which is the mass of the system is included the car and the hanging weight. We're going to keep that at control. And what we're going to do is we're going to change the amount of weight that we have on the end of the hanger. And the way we keep the system mass at control but change the weight on the hanger is whatever weight comes off of the hanger has to go on to the cart. So we have to make sure that we're constantly moving weight from one place to another to make sure that we're not changing the mass of the system. And the other sets of groups are going to check and see, change the mass of the system, but keep the weight of the hanger exactly the same. So what we're going to do is, in that case, we're just going to keep adding mass to the car. So that way, if there's more mass added to the car, then the weight of the hanger stays the same. So we're going to make a hypothesis for each of those. So whichever one you have, go ahead and pause the video and make a hypothesis statement as to how you feel the acceleration is going to change based on those changes, changing the weight of the hanger or the mass. Right. So for this video, this data collection, what we're going to do is we're going to do the low-tech version where we don't have any of these fancy gadgets and sensors that we're going to use. So what we need to know is that this cart is going to travel in the direction and accelerate until the mass hits the ground. So what we need to know is that the mass is 0.91 meters above the ground. If we know that it is 0.91 meters above the ground, what we're going to do is we're going to use kinematics and we're going to calculate the acceleration. So we're going to go to the whiteboard and we're going to see how we're going to do. All right, so what we're trying to find is the acceleration of the hanging mass cart system. So the information that I know is about the hanging weight, and the hanging weight is 0.91 meters above the ground. It hits the ground. It starts from rest, and what I'm looking for is the acceleration. So of the variables I have remaining, I have the final velocity that it hits the ground with and the time. Of those two variables, the easier of the two to find would be the time, because we can just use a stopwatch to calculate the time. So what we're going to do is we're going to use our kinematics and an equation that does not have our final velocity in it. And if you're using your AP formula sheet, the AP formula sheet has the second kinematic equation. Now, because it's accelerating downward, I changed that plus 1/2 AT squared to a minus 1/2 AT squared. So now what I'm going to do is I'm going to solve for the acceleration. So I know that the Vy naught times t is 0 because my initial y velocity is 0. So 0 times t gives me 0. I also know that my initial height is 0.91 and my final height is 0. So I'm going to change that to negative y naught equals negative 1/2 AT squared. And I'm going to multiply both sides by negative 2. And then I can solve for my acceleration. So when I'm done collecting my data, I'll have a bunch of time data. And what I'm going to need to do is I'm going to take that time data and I'm going to use this equation here and I'm going to solve for the acceleration. So I'm going to convert times into acceleration, knowing that it falls 0.91 meters, and I will collect the time values in order to calculate my accelerations. All right, so that's a lot of information to throw at you at once. So we're going to recap that. So what we're doing is we're changing the mass of the system. The system, remember, is the hanging mass along with the car's mass, and we are going to calculate the acceleration. So remember that you're going to end up with a data table. You're timing this mass as it falls. So you're going to have a data table where you have times from the hanging mass falling, it's 0.91 meters. And from that, you're going to use the kinematic equation I just showed you how to derive the acceleration. So you're going to calculate the accelerations. Then you are going to have the mass of the system. So the mass of the system is the mass of the car plus the mass of the hanger. So we're just going to put a little subscript of S for mass of the system, and that is going to be measured in kilograms. Once you have your data table completed, what you're going to do is you are going to plot a graph. So that graph is going to be graphed with the acceleration on the vertical axis and the mass of the system on the horizontal axis. Then from your graph, you are going to match that up on your graphical method summary sheet. You're going to create a straight line graph. Remember, no curve fitting. We only do linear regressions. So we're going to create a straight line graph of this data of acceleration versus mass. Then from that, we are going to write our mathematical model. So you are all set now to go ahead and collect some data. All right, so now it's time to run some trials. Let's go ahead and collect your data. Due to the length of this video, we're going to go ahead and look at the lab results in a different video. So I hope you have a great day and an even better tomorrow. If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @Cavi Coaches.